I know. I have to. I have to. All right. Oh wait, where's? Okay, now we got 45 minutes to do the final. Summer final is described as Larry, Curly, and Moe. We are in the version is printed at the bottom of page 11. We are not going to do the multiple choice. That will be done by me tomorrow, and then I'll repost that. If you have any further questions about multiple choice, we can answer that on Thursday or Friday. Okay.
So do we need to study the multiple choice from all the tests, or is there another one, like another bank for the final?
I would say that the bank for the finals are probably 80% of what you have. I'm gonna get you to, two hands? I'll be with you in a moment. Oh, you're stretching? You're not getting robbed or anything? Okay. The multiple choice is gonna see some changes. Some. When I was going over the multiple choice, I found it fairly repetitive to what we covered on the tests. I would say there are some people that did. Someone showed me the other day, there's some student service where you can input your multiple choice questions and then share them with other students. Quizzy, yeah. Quizlet, that's it. And some people have taken all my tests and the multiple choice and put them together in a Quizlet. And I'm like, that's amazing. And some people have said, yeah, I just sit and watch TV and I play that Quizlet game. And I'm like, well, that is kind of what I call studying. So I'm fine with that. I'm gonna add a few wrinkles to it. I'd probably say the bank of multiple choice is now up to like 175, and I may add another 25 or something. I've seen a lot. The thing about the multiple choice.
Are you saying add 25 new ones to the final?
Yeah.
That
But remember that you've never seen. But oh, they look all sad. Don't look sad. The advantage is, and this is why someone came in. You may have heard it, sapling. All right, there's rumbling, and so now I got to put down a revolution. When you answer 175 in my multiple choice, you start hearing my voice, you start seeing my logic, you start getting used to it. So if I gave you a new set of 25 multiple choice, you'd probably go, oh, that's a lot like this, or this is a lot like that. We've been together for 3 or 4 months now. This stuff shouldn't come as a surprise. That string multiple choice stuff, inclined plane, I noticed that wasn't in the multiple choice for the final. I may put that back in. I want a lot more graphics to be in. Like take a picture and go, what's that? And have an equation associated. Stuff like that. You're welcome. All right, problem 1. And once again, this is the Larry version. Okay, this is similar to the one that we did this morning, but appetizer. It's a Bernoulli's equation. Fluid comes from one point, goes down. Area changes. Velocity will change. I want the answer in meters per second. Pressure will be in atmospheres. First thing you need to do is equation of continuity, A1 V1, A2 V2. I need to know what V2 is. That's A1 V1 over A2. I was very nice in this equation. I gave you the areas straight up, 0.8, 0.4, and 8. So the velocity is 16 meters per second. So as you can tell, this is something where I was taking the time and figuring stuff out. Hopefully the pressure will be nice as well. You need Bernoulli's equation for this. I use the bottom part as having a height of 0, so H2 is 0. I'm looking for P2, so this is P1, and I'm going to write this a little bit well. I'm going to factor out a rho. Fluid will be water, well, unless I say otherwise. It's not mentioned here, but it's water. Rho GH1 plus 1/2 rho V1 squared minus 1/2 V2 squared equals P2. Now remember, hold on. The pressure was given in atmospheres. The answer was asked for in atmospheres. These terms will produce newtons per meter squared. So what you need to do is use the conversion. So P1 is 3, rho is 1,000, G is 10, H1 20, 1/2, V1 8, 1/2, V2 16, and this is all over 1.013 times 10 to the 5th. And hopefully I won't get a bizarre negative number. Yay, it's not going to be negative. Unlike test 3. So the answer is 4.03 atmospheres. This is a little more difficult to do. I'd have to take a lot of time and get numbers to work out with 1.013 times 10 to the 5th. But in the end, it did work out. Close. Oh wait, let me. So for problem For problem 2, wait, let me get this. All I wanted to know for appetizer number 2 is the moment of inertia of this system. Now, to look at this, the radius is 2 meters, the mass is 1,000 kilograms. I give you the mass of the stick, and then the length is 3 times the radius of the disc. Now, to speed things up, we've got a stick that's rotating about, not at center of mass, but at the edge. And so the moment of inertia of this stick is 1/12 ml squared plus m d squared. Parallel axis theorem. D in this case is L over 2. Common factor of 12. And 1/12 plus 3/4. Oh, I'm sorry. One-twelfth and plus 3/12 is 4/12, which is 1/3 ml squared. So the stick itself has a moment of inertia of 1/3 ml squared, where this is the mass of the stick. The moment of inertia of a system is the moment of inertia of the stick plus the moment of inertia of the disc. Stick 1/3 ms L squared plus 1/2 mr squared. Moments of inertia of stick about its center of mass, disc about its center of mass, and a point rotating about a center will be given. Parallel axis theorem will be given, which is that. Now, the one thing that I didn't give you was that the length of the stick was 3 times the radius of the disc. The radius of the disc is 2, so 3 times 2 is 6. So it's 1/3, 100, 6 squared plus 1/2, 1,000, 2 squared. Parallel axis theorem if, and this is how, one of the things I need like one of the bad things about lecturing here is that I can't just grab stuff out of the demo room. If you take who asked the question? Okay. When you take a pen and you rotate it like this, there's a certain amount of force or torque in reality required to flip that pen this fast. When you put it and try to rotate it like this, it's a little bit harder. So when you're rotating it like this, you're putting a little bit of effort into it, but that's kind of trivial. So what's the difference between this and that? It's the same geometric shape, but different orientation of mass about the rotation point. So when you have something that's not rotating about its center of mass, you've got to use the parallel axis theorem. to calculate that moment of inertia. Okay, next. Atwood's machine. I'm only allowed to use the equations of energy. It's kind of a side note on the fluid thing. With the hole in my bucket problem from test 3, it was intended that you use Bernoulli's equation in order to derive the velocity of the fluid coming out of the bucket. However, it wasn't mentioned that you were restricted to only using Bernoulli's equation to derive it. Some students came up with the idea and asked me later if it was a correct solution, and I said, well, if I said you couldn't use it, it's correct. I made explicit mention in the lecture itself, because we did that problem, that the fluid coming out of the hole of the bucket was the same velocity as if you dropped a rock or an object from the same depth. So fluid that's 2 meters under the surface comes out at a velocity if you had just dropped the rock. And so what they had done is that they had calculated the velocity of a rock using the equations of energy. And they asked me if that was a correct way of doing it. And I said, if I didn't restrict you from doing that, it's perfectly allowable. Here, I restrict you to only doing using the equations of energy. It's initially not moving. Its final velocity is 20 meters per second. I think that if I do give that bucket problem again, well, I don't think it would be exactly like that, but if I did it again, I would require that you use Bernoulli's equation. So I would definitely go over that. The energy initial minus the work removed through friction is the energy final. There is friction. We're looking for mu sub k. Once again, this final, we all know things that really that get me interested in talking about physics. You know vectors, and you know algebraic manipulation. And it's all about the setup. That's why when the whole version of test 3 for the bucket came out, or I'm sorry, for the Atwood string came out with the negative answer, the graders had the easiest time grading it if you did it algebraically and showed the correct algebraic solution, because then they know you know what you're doing. With this, the initial energy is potential energy, M2GL. The work removed through friction, sum of the forces in Y is equal to 0, which is equal to normal force minus mg. Normal force is equal to mg. Friction force, which is mu sub k. Normal force is mu sub k mg. Work, force times distance is mu sub k mgl. And that's the work removed through friction. The energy at the final point, both objects are moving as 1, so you can write 1/2 m1 plus m2 v squared. And I know it's a little bit scrunched, but what I'm going to do is I'm going to move this over here and this over here. m2gl minus 1/2 m1 plus m2 v squared is equal to mu sub k. M1, pay attention to your subscripts, GL. And then all you got to do is divide out the G and the L. I would just keep it like this. And that's it. So should I have provided numbers which produced a negative answer, a nonsensical answer, the graders looked at something for just this, and if they saw this, they just gave full credit. For us, oh, there was one other thing that we needed to do. M2 is 1/4 M1, or 4M2 is equal to M1. 6 of one, half dozen of the other. 1/4M2 GL. M2 GL minus 1/2 4M2 plus M2 V squared. One extra line of stuff we could go into. 4M2GL, M2GL minus 1/2 5M2 V squared equals mu sub k. Now there's an M2 here and M2 there. I could factor it out and divide it by that M2 there. So all of those will cancel. And to write it out cleanly, and that's that. So this is 1/4 times 10 times 20. Why is it 5 and not 4? Well, I wrote M1 is 4M2. 4M2 plus M2 is 5M2. Okay. L is 20, G is 10, L is 20, minus 5/2 20 squared. As you can see, there are a lot of 20s rolling around in here. 200 minus, please let this work out, 2.5. Whoa. What did I do back then? I think I may have changed a number on the fly. Well, okay, let's just do it. Does anybody have problems with the algebra? I need to recall. What I need to do is keep notes from when I actually gave the test, because I may have changed a number. Because I have a bad feeling about this.
What'd you get?
I got -1. Yeah. So
I didn't do it.
one of two things either happened. I either had to sit here and go, you know what I probably did is And this is one of the things that I would recommend on a final. Or when was this final given? This was the summer final. On a summer final, what we had to do was the third test was given on a Friday. No, it was given on a Thursday. We did a review for the final on Friday, and then we gave the final on Monday. So it moves very quickly, and I wasn't able to check the numbers right. I think what I did was I just announced to everybody, all right, V is now 2 meters per second, and that would have changed the number dramatically.
Why did you change them all to M2 instead of to M1?
Flipped a coin. It doesn't affect, it affects nothing. And also one of the things, a lot of times, a lot of you sit here and go, well, he got it wrong. He got a negative number, so all of physics is wrong. Let's look at this equation right here. G times L meters, hold on, let me get a new. G meters per second squared, L meters minus V squared, meters squared, second squared, over meters per second squared meters. This gives you meters squared, second squared, in the denominators, meters squared, second squared, nothing. So the units work. It's just that I didn't pick the right number. I think, now that I'm trying to think about what I did on the final, I may have told the class, don't use 20, use 2. And then that would have changed the number to, let's see, 2, 4 times 5, 20 divided by 2 is 10. So that's 190 divided by 4,800. Then I would have gotten an answer. If V was 2, mu sub k was 0.2375. So if you changed it. One of the things that you really want to do on the final is not bail after only an hour and a half. Because what's going to happen is there's going to be a lot of students trying each of the problems, and in the unlikely event that a problem is not correctly constructed, I'll have to call an audible and make a change. It may have been during the final I said, all right, I'm going to give you a hint on the answer. Coefficient of friction is negative, and it's a whole number. And I think that would have been enough to fix the problem. It's a number. My opinion of numbers are very low. It's about the physics. The units work. I have faith in the equation. It's just that I didn't choose the wrong numbers, assuming. Any questions on this? Yes?
Did you say you changed the 20 to 2?
If you use 20, the answer is -1. If you change V to 2, it's 0.2375.
Not -4.
You got negative. No, you couldn't have gotten -4 off of that. 0.2375, so we have confirmation. If V goes to 2, that negative number within the parentheses gets a lot smaller. It goes from big number to smaller. A lot less than 200. So it should be fine. And so one of the things that the first year, the second year that I gave tests, there was always a problem wrong. Always. And let me tell you something else. On my, when you go into graduate school, you take 2 years of class and then you take the comprehensive examinations. And if you fail the comprehensive examinations, they go, bye. on the electrodynamics and optics exam, there was a problem where the proctor, my own advisor, told me it was a correctly constructed problem until after 2 hours of the 3-hour comp. And then he went, whoops. You got to learn how to just roll with it. And I go, okay, fine, he's just gonna give us the points and then we move on. So with the, and I carry that belief system over to you guys. If I make a mistake, don't let it rattle you. I'm going to fix it. So you should have enough faith in me to hang with it. All right, any other questions? Because I know it's finals, which means only one thing. You guys are going nuts. Problem 2. And really, there's, multiple choice mistakes, big deal. There's only been one problem mistake all semester. Whoa, back up. Give me force at the fulcrum, give me tension of the string. Classic torque bar problem. Sum of the torques is equal to 0. There will not be a right-hand rule game. It will be in something like this. I'm going to choose the rotation point as this. That means M1GR1 as torque 1, torque 2, M2GR2, torque 3, tension R2 plus R3. Really, we're only that far? Amazing. All right. Left, down, up, positive. Right, down, in, negative. Right, up, positive. So those are the signs. F is at the fulcrum. It doesn't count because its radius is 0. M2GR2 minus M1GR1 TR2 plus R3. And that's the tension. 10, 20, 3, 1, 2. Also, you notice that M2 is huge because there was one time, I think I used 2 and then tension was negative. So I was ultra paranoid at the time. R2 is 3, R3 is 2. 60 minus 2 is 58 times 10 is 580. 580 divided by 5. 116 newtons. Also, they're not gonna hit you hard for units. They will ding you for units. So if you miss a unit, they'll take a point. So remember, tension, force, newtons. Now to get F, sum the forces vertically. F plus T minus M1G minus M2G. I'm looking for F, M1G plus M2G minus tension is force. So minus T minus 116 plus 1 times 10 plus 20 times 10. 210 minus 116, 94 newtons. So that is the torque bar problem. All right, what we're gonna do is we'll do, this is really weird. We did the multiple choice this morning and we're still taking up the same amount of time. All right, we're gonna do number 3. And then because we're running short on time, we're gonna end it with number 3 and then we're gonna continue with 4, 5, and 6 on Thursday. Okay, 4 meters at 270, instant conversion to what vector? You should just shout it out. Negative 4y hat, correct. So A is negative 4 y hat. B, it's a second quadrant vector. We're looking for negative x, positive y. Drawing it out. That is the reference angle, which is 120. Or I'm sorry, that's not reference, that's absolute. Reference angle is 180 minus the absolute for a second quadrant, 180 minus 120, which is 60. BY, BX, BY, B sine, theta reference, BX, B cosine, theta ref. B is 6. Can't see. Hold on. All right, now that we're done with this, I'll take that out. 6 sine 60, 6 cosine 60. Cosine of 60 is 1/2, so that's 3. 6 sine of 60. 5.20. All right, those are just the magnitudes of the sides. The B vector, 3 and 5.2, because it is a second quadrant, the x is negative, but the y is positive. That gives you a negative 3x hat plus 1.2 y hat. And that's C, that's the resultant. If I make this problem a appetizer, which could happen, in the morning final it was, I think, I would only ask for the resultant. Because it is a regular 15-pointer, I want the equilibrant. Equilibrant just flips signs. And you get that. And if we're gonna be picky about it, which my graders will be for units, wrap them in parentheses and put the meter on the end, because these are displacement vectors. To calculate the polar, C goes negative, positive. It is a second quadrant angle. Theta absolute is 180 minus the reference angle, which we don't know yet. The reference angle is inverse tan of CY over CX. use magnitudes when doing this. Do not use negative signs when calculating this. Sometimes it works, a lot of times it doesn't. So my theta is 158.2 degrees. And because my resultant angle is 158.2, to get the equilibrium, you add 180 and it's 338.2. The magnitude of C, Pythagorean theorem, doesn't matter if you use signs or not, because you're squaring them and it goes away. .23 meters. So that will give me C, 3.23 meters at that, and D, 3.23 meters at that. Because just as C looks like this, D is the same magnitude but 180 degrees in direction. And so that is that. What we're gonna do on Thursday is 4, 5, and 6. And then delve into another final, and that's it.